Hello everyone, and welcome to another episode of BMED 202. In this episode, we will look at using the Polygon of forces method to solve for resultant and equilibriant forces. This method is mainly used for solving, or can be used for solving the equilibriant, or solving for the equilibriant force, but in turn can be used also to solve for the resultant force, since we already know that the equilibriant force and the resultant force are of same magnitude but in the opposite direction. So once we find the equilibriant force, we're going to simply flip the direction and use the same magnitude. Right, so let's dig in. So we are going to do two exercises today so that the concept is cemented in a more concrete way. Now, let's start with this one. So let's copy this one into its own space. And you would have already known, or you should already know how to generate this diagram. Okay, so let's start. It's pretty simple. It's the same step as the triangle of forces. It's just that you're not going to get a triangle. Now, let me explain something. If these forces are in equilibrium, meaning if these forces acting on the body is already bringing the body in a state of equilibrium, then you will indeed get a triangle, since there are three forces. If there are more than three forces, you will get a polygon. If there are four forces and the body is in a state of equilibrium, you will get a closed quadrilateral. If there are five forces and the body is in a state of equilibrium, you will get a closed pentagon. Now let me try to determine if this body is in a state of equilibrium by using the same method. Now, as before, we can start with any vector. But in doing this now, since there are three forces, you have to now choose the forces based on which one comes next. So let's say we're going to start with the middle force. We're going to copy this vector. So I'm clicking the starting point. It ends here. So the force starts here, ends here. I'm going to select any other one. If I'm selecting this, it simply means I'm going into a anti-clockwise direction. If I'm selecting this, it simply means I'm going in a clockwise direction. So let's go clockwise. So this is the next force. Copy. Meaning clockwise as it relates to selecting the force. So I'm selecting this one next. I'm placing it here. Sorry, did something wrong there. I'm supposed to place it at the top, the end of the previous force. Let me delete this. I didn't mean to copy this. Now the third force here. Now it may seem, given the fact that there are three forces, that it still doesn't matter which forces you select first, because if you select this one, then this one, then this one, you're going in a clockwise direction. If you select this one, then this one, then this one, you're still going in a clockwise direction. If you select this one, and then this one and this one, you're going into an anti-clockwise direction. Now, if you select them randomly, it will still be in a particular order, in a particular direction. That's just because there are three forces. If there are more than three forces, you now have to pay attention to the one you're selecting next, as will be demonstrated with this force, or these number of forces acting on this particular body. Now let's double check to see if everything is okay. So we started with this force. Yes, it's going in that direction. Then we went to the second force. which is going in this direction. Then the third force, this direction. Please note that you will not always get a perfect polygon. Some of the lines may overlap. So as a result of these three forces, you are now getting this force or this result. Now, remember what I said? If the last line, the ending point, is not touching the first point that we started with, then the body is out of equilibrium. Once we connect this last point now to the initial point that we started with, that will now give you our equilibriant, and the direction will be based on the last point, meaning this will be the starting point of the equilibriant and the ending point. Thus, this is the direction. So let me copy this equilibriant, and I'm going to add it. So the equilibriant force, in order to keep this body in equilibrium, will have to be here. And you can go ahead and measure the direction. Now this equilibriant force needs to be 117.42 or 0.43 rather, if we're rounding to 2 decimal places. 117.43. Now this polygon is a very weird polygon. Let's draw this again just to demonstrate that it doesn't matter the which one you start with. Let's start with this one, and we're going to actually go the opposite direction, meaning we're going to select the vectors in an anti-clockwise direction. So this is the first one, and we selected in a clockwise direction first. So we are going to select this one now. So at the end, then we are going to select the third one now, which is this one. Copy. Now in this case, you still realize that you are not getting an enclosed shape, and this is as a result of the fact, as a result of the body not being in equilibrium. So now the equilibriant force will now be this line, and as you can measure, as you will realize, this will be the same length there you go, the same length, and it is going in the same direction because you're following the pattern clockwise. Well, this in this case is clockwise. So we selected the fourth. Oh, we selected in a clockwise direction. We selected this first, and this first. So we're going in this direction. As I was saying, it doesn't matter which one you start with first and the direction, whether you go anti-clockwise or not, you will still end up with the same resultant or same equilibriant. We're solving for the equilibriant here. This is the equilibriant. So just to recap so far, or to reiterate a point, the polygon of forces method is used to find the equilibriant force, because the equilibriant force is the force that will close the polygon. If it's a case where you connect all the forces involved and the polygon is closed even before solving, it means that the equilibriant force is 0 and there's no need for an equilibriant because the body was already in equilibrium. Now, in order to find the resultant force, all we have to do is copy this force, place it on the drawing, let me copy this drawing. But if you notice, the force is overlapping. This is simply because the resultant force and the equilibrium and one of the particular forces are in the same direction. So as to not confuse you guys, I could have still just placed the arrow head. Let me change this to resultant. But you're seeing some, well, it's not a perfect overlap, as you can see. But just in the event you get a perfect overlap, let me show you an alternative way that you can represent it. So this is the resultant force, which is opposite to the equilibriant force. Let me copy this drawing again to show you how you can illustrate it. All I will do is take this force, move it, put it in the opposite direction, and move the arrow. So I'm going to place the arrow somewhere about here. So if you realize, now I'm using it's showing as a pushing force rather than a pulling force. So this is the resultant. You can use this. I like how this looks because you can still see that it's not going in the same direction. If this resultant force was shorter and it's now hiding, then you can definitely use this method to show the forces. Right? So let's move on to the final force. Same method. And I'll show you definitely, let's delete this out of the way, we don't need this anymore, that you now have to choose the forces in a particular order. So let's start with this 66 newtons. Copy. Now, the next force that we are going to select, we can select either force on the side. If you're selecting anti-clockwise, we can select the 77. If we're selecting clockwise, we have to select the 33. At no point we can select this because we started with this. If we started with the 33, we cannot use the 77 because it's not next either clockwise or anti-clockwise. So let's go anti-clockwise. So if we selected the 66, we now have to select the 77. And we're going to start it where the first force ends. Or end, yes. So let's get these out of the way. I didn't want to select these. The third one in the series, anti-clockwise, is the 44. Then it's going here. And the fourth one is the 33 newtons. And we connect it at the end. Now, since the polygon did not close like the previous drawing, this body is not in equilibrium. So the body is here. 4 forces are acting on the body. One pulling here, one pulling here, one pulling here, one pulling here. The body is going to move in a particular direction due to the fact that the body is not in equilibrium, which we have just proved over here. So now we are going to connect. We're going to draw our equilibriant line. And then put the direction. This is the equilibriant. Now this is the force that is required to bring the body in equilibrium. So let's just put it over here. So this is our equilibriant force. Let's see if I can. All right. And this equilibriant force will be 29.37. So this 29.37. All right. So this is, once I've found my equilibriant force, let me copy this again. I can get my resultant force, which is a force that is equal but opposite in direction. Let me show you how you can transfer this to a resultant force. I'm going to rotate, but I'm going to rotate 180 degrees. So you can click the rotate command and type 180. By default, AutoCAD is set to recognize a positive direction in an anti-clockwise motion. So if I had typed a negative number, then it would rotate clockwise. If I had typed a positive number, it would have rotated anti-clockwise. But in this case, it doesn't matter. 180 degrees clockwise or anti-clockwise will give you the same result, which is equal but opposite. So now this is my resultant force. If you are not comfortable with doing it this way that I've just illustrated, meaning rotating it, then you can just do the method that I used, the method that I showed you before. Okay, so I didn't want to delete that, just this. So this is the resultant force, which is opposite to the equilibriant force that we used the polygon of forces, to solve. So let's recap. So we use the polygon of forces method when we have 3 or more forces acting on a body to find the equilibriant. The last force that will close the polygon will be the equilibriant force, and we can use that force by flipping it, meaning changing the direction by 180 degrees to get the resultant force, which will be of the same magnitude. Right? If you were trying to get the polygon of, if you're using the polygon of forces method and all the forces involved created a polygon that was already closed, you will have no need to solve for the resultant and equilibriant forces, because by the drawing being closed, it is showing or proving that the body is in a state of equilibrium, and as a result of that, the resultant force would be 0, and the equilibriant force, which is the force that is needed for the body to be in equilibrium, will also be 0, because the body is already in equilibrium. So it doesn't need any additional forces to bring the body in a state of stability. Now, I hope you guys learned the concept. Please rewatch the video to cement the concept. Please also watch the previous video on when I was using the traditional method in explaining, because I provided more information on that. So like, share, subscribe, stick around for future videos. Have a good day.